Okay, so there are dozens of Laplace. You can just Google a Laplace table. There's one in your book. There's one in the Schwarm's outline and one in the Zill book. So you don't have to use my table. In fact, I'm not even sure this is the best looking table. But here's our original function. Over here on the side is the Laplace transform of that. Typically, the way we'll be doing it, though, is we'll have something that looks like this, and we'll try to match it up going backwards over here. So that's the way we're going to be using the table, is we'll have something that looks like this, and we'll go, oh, that is the Laplace transform of this guy here. Okay, so some notes first. The Laplace transform is a linear operator. Linear means distributes. That's what it means. The integral is a linear operator because limits are linear. That's where everything comes back to limits. Everything in calculus comes back to limits. But the linear, or the Laplace transform, is linear. So the Laplace transform of, say, some alpha function f plus beta, some function of g, I can distribute and I can factor out constants. So if I wanted to find the Laplace transform of a bunch of stuff added together, I just distribute. I just do it one piece at a time. And the Laplace transform of derivatives. The Laplace transform of, say, y prime, well, let's stick with f for now. F prime of t is by definition the integral from 0 to infinity e to the negative st f prime t dt. That's just begging to be integrated by parts. That's an integration by parts problem. That will be, like, I'm not going to go through all the details here, but you guys should check this. That is e to the negative st f of t. Now f prime, I took the antiderivative of this one and the derivative of that one from 0 to infinity plus s integral 0 to infinity e to the negative st dt f plus f. Wait, that right there, that is L of f. That's the definition of L of f, which we tend to call capital F of s. When I plug in my limits here, as long as my function doesn't grow too rapidly, this guy is going to dominate this guy. So as long as f of t is of exponential order, then the exponential will dominate, and when we go to infinity, this will go to 0, and this all becomes negative f of 0. So what do we mean by exponential order? Exponential order means you don't grow faster than exponentials. It means literally what we need to happen here, that this exponential will dominate this function. So this guy might be growing. It might even grow like an exponential, but this one will shrink faster than this one will grow. And in all the examples we do, that will always happen. It's pretty hard to grow faster than an exponential. Okay, so what does this turn out to be? This means that if you have some derivative, some y prime, the Laplace transform of y prime is s times capital Y minus y of 0, where capital Y is the Laplace transform of little y. You got to keep your lowercase and your uppercase separate here, or you're going to have a bad day. What if we had two derivatives? The Laplace transform of y double prime. We could go through all the math, but I'm just going to spit out the answer for you here. Is s squared capital Y minus s y of 0 minus y prime of 0. In general, the Laplace transform of some nth derivative is s to the n times capital Y. And now the s's are going to go down as my derivatives go up. So Sn minus 1 y of 0 minus Sn minus 2 y prime of 0 dot 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 all the way down to y n minus 1 of 0. So the powers of s go down, the initial conditions go up, starting with capital Y, initial condition of the original function, initial condition of the first derivative, second derivative, and so forth. As the s's go down, the derivative order goes up.